Okay, so last time uh, we looked into some definitions, right? So we looked into circuit, what is a circuit, then the Moore's law, right? So the Moore's law is as the time increases, the amount of information also increases, and this increases is a log scale, right? And it's a linear. As you can see in these different examples, first would be the example of transistors or the microprocessor transistor counts. Second would be say a clock rate, right? So the processing speed of an CPU. And what is an analog circuit? What is a digital circuit? Uh, and some definitions like binary and multi-valued levels, right? The next thing which I asked you to read is the same uh, PowerPoint and some slides on the elements, right? Digital logic elements, right? So I'll go through them, and these are like the uh, uh, basic basics in digital logic, right? So this is where things start from uh, with um, with digital logic, and those are these gates, right? So we briefly looked into what are these gates in the last class, and essentially it's just as the name suggests, right? It's a structure which allows and which prevents from passing some information, right? So that's a gate, and because we are using some logic, right? So we have a logic or a reason why we want to allow some information to pass and some information to prevent. That is the reason we call them as logic gates, right? So the logic gates they also have um, uh, they also have named these gates these with the names like and, or, not, nor, right? So so the gates can be say and gate, right? So this and that, or the gate can be an or gate, this or that, or it can be a not gate, this or not that, right? So it's exact opposite. So so let's look into these logic gates. I mean, I want you to understand what these gates are, and these truth tables, right? Okay, so the truth tables. Um, so in the exam, I would ask you these truth tables because these are like, as I said, these are like basics of this subject. So I want you to understand and um, and make these truth tables, right? So in the exam, you uh, so in the exam, I'll ask you some questions on explain the AND gate, or explain the NOR gate, or explain the OR gate, right? So these are the truth tables, right? So they're called truth tables because this is what the things will six things will look like, right? When you have two variables, say X and Y, right? So if you have like one variable called X and one variable called Y, and if you apply a gate called AND, then this is the output you would expect, X and Y. So the output in this third column is what you should expect when you have these two variables X and Y with an AND gate, AND gate, right? So similarly, if you have two variables X and Y, and you apply a OR gate, you get this output, which is different, right? And similarly, if you have just one variable, say X, you apply NOT gate, you get this output here, right? So essentially what we're trying to do is we're just trying to take in, say, two variables, X variable and a Y variable, and we are applying some gates. First gate is AND gate, second gate is OR gate, third gate is NOT gate, and we are expecting an output. So I'll explain you what output and how do you calculate that. But this is what we are doing in this slide, right? So we are taking some variables and we are trying to use those variables to generate an output by applying these three logic gates. First is an AND gate, second is an OR gate, and third is a NOT gate. Now you can see that there are these diagrams here, right? So these are some diagrams here. So this diagram is like a blunt bullet, right? It's a bullet diagram. It's a blunt bullet, right? I call it as a bullet, blunt bullet. This is a pointed bullet diagram. This is an arrow, right? So these diagrams are very specific to these gates. Say AND gate, right, would have this diagram. So whenever you see in this diagram, it's an AND gate, right? It's an AND gate. Whenever you see this diagram, you say that it's an OR gate. Whenever you see this arrow diagram, it's a NOT gate, right? So it's just to make things simpler, right? So it's just these diagrams have been made uh, to make things simpler and to visualize things, right? So people usually use these three diagrams for these three different gates. Now, if you go into these truth tables, right? So first variable is X, second variable is Y. So first column is X, second column is Y. Third column is the output of that gate, right? So the third column in this is AND gates, which is an output of AND gate. So if you have zero value in X and zero value in Y, you would have zero value in output of X and Y. So you calculate this by multiplying X and Y, right? So 0 multiplied by 0 is 0. That's so you just, if you multiply things, it's an AND gate. If you add things, it's an OR gate. Okay, so 0 multiplied 0 is 0. Say if you have 0 as X, 1 as Y, 0 multiplied by 1 is 0, right? So 0 is your output. If you have 1 as X, 0 as Y, 1 multiplied by 0 is 0, 0 as X and Y output. If you have 1 as X, 1 and Y as Y, 1 multiplied by 1 is 1. So 1 is the output, right? So simple. So if you have an AND gate, you multiply things, right? So 0, 0, 0. 0 multiplied by 1 is again 0. 1 multiplied by 0 is again 0. 1 multiply 1 is again 1, right? So, and you multiply things. Or gate, you add things, right? So 0, X, 0, Y, 0 plus 0 is 0. 0, X, 1, Y, 0 plus 1 is 1. 1, X, 0, Y, 1 plus 0 is 1. The last thing here is an exception, right? So the last thing here is 1 as X, 1 as Y. So 1 plus 1 is 2, but you say it's 1, right? So it's an exception. Instead of 2, you just, it's a binary, right? So you have to have output as 1 or 0. So 1 plus 1 is 2, but binary of it would be 1. So you say it as 1. Okay, do you have any questions? Do you understand what I'm explaining here?
Yes, sir, I understand.
Understand? Yeah. Emanuela, do you understand? Are you there? Emanuela,
Yeah, I'm here.
do you understand what these truth tables?
Yeah.
Okay. So if you see an AND gate, you multiply. If you see an OR gate, you add, right? And the last one is NOT gate. In NOT gate, you just take opposite, right? So if X is 0, the NOT of X would be 1. If X is 1, the NOT of X would be 0. So you just take opposite value of your X variable, right? So that's it. So these are logic gates. So it can be AND, it can be OR, it can be NOT. You have to remember the diagrams. AND gate is I usually remember it as a bullet, but it's a blunt bullet, right? It's a blunt bullet. OR gate is a bullet, but it's a pointed bullet. NOT gate is an arrow. It's an arrow, right? And the truth tables, in AND you multiply, in OR you add, in NOT um, you take uh, you take opposite, right? So that's your three gates. Now there are more gates, right? So there are more than three gates. There is a NOR gate, there is a NAND gate, which I'll explain you in the later slides. But then for now, you just remember these three gates. These are the most important and most frequently used gates, right? So people often use these three gates. The other gates are little, they are used not as often, right, as these three gates, but you should definitely know these three gates and these three truth tables. I'll ask you these 6 questions in the exam, right? So I'll be asking you these 6 questions, the diagrams and the truth tables. Okay, moving on. So logic gates, they can also be presented as these waveforms, right? So you see these waveforms here. So this is X, this is one wave, second wave, third wave, fourth wave, fifth wave. The first wave here is for a variable called X. If you see a 0 value, it's a depression, right? So wherever you see a 0 value, it's a depression in a wave. Wherever you see a 1 value, it's an elevation, right? So it's more simpler than these other structures. So wave is, when you see 0, it's a depression. When you see a 1, it's an elevation, right? So if your X variable is 0, so it's a depression. 0, depression. 1, it's an elevation here. 1 is continued elevation here, right? So X is presented in this waveform where zeros are depressions, ones are elevations. Y is 0 depression, 1 elevation, 0 depression, 1 elevation, right? So again, we have to make a kind of truth table, right, in form of a waveform with two variables called X and Y. Three gates, first is AND gate, second is OR gate, third is NOT gate. For AND gate, you multiply. So 0 multiplied by 0 is 0. 0 multiplied by 1 is again 0. 1 multiplied by 0 is again 0. 1 multiplied by 1 is 1, right? So you have output 0, 0, 1, 0, 1. And to present that, 0 is depression, 0 is depression, 0 is depression, 1 is elevation, right? So it's just a different way of presenting your truth table, right? And this presentation is called waveform, right? Second is OR gate. OR gate you add. So 0 plus 0 is 0, depression. 0 plus 1 is 1, so it's elevation. 1 plus 0 is 1, so it's elevation. 1 plus 1 is 2, but in binary you take it as 1. So it's a continued elevation. So 1, 1, 1, it's an elevation, right? 0 is a depression, 1, 1, 1 is elevation. Not of X, right? So if you see this value here, it's an X complement, right? So it's an X complement or not of X. So there's an X with this complement symbol here. You see this small symbol here, right? So this is a very unique symbol to present not of X, right? Opposite of X. So X variable here you have 0. So opposite of 0 is 1. X variable is 0. Opposite of 0 is 1. X variable is 1. Opposite of 1 is 0. X variable is 1. Opposite of 1 is 0. And What's that? Are you saying anything you want to tell me, Lydia? Any question?
Oh, no. I was just letting you know I was here.
Okay. All right. So that's your NOT gate, right? So NOT gate is exact opposite of your any variable. So 1, 1, 0, 0. And 1 is an elevation, 1 is an elevation, 0 is depression, 0 is depression. That's it. So that's your waveform, right? So if you have any questions, please ask me, right? So I will be asking you to these diagrams, 3 questions on these 3 diagrams, 3 questions on these 3 tables, and 1 question on this waveform, right? So I will ask you to make this truth table and to represent it in a waveform. So you should understand that you just have to convert zeros to depressions and 1 to elevations, right? That's all. So the next thing we want to look into is this another gate called Nand gate, right? NAND. So new gate. So we know what is an AND gate. We know what is a NOT gate. So if you combine a AND gate with a NOT gate, it's a NAND gate. Okay. So N from NAND is for NOT, and AND is for AND, right? So NAND is NOT plus AND. Okay. So I want you to know this structure here, right? So if you remember, the AND gate here is a blunt bullet, right? It's a blunt bullet, right? It's a blunt bullet. If you add a circle in front of this blunt bullet, it's a NAND gate. That's all, right? Do you see this small circle here in front of this blunt bullet, right? So I call it as a blunt bullet. In front of this blunt bullet, you add a small circle, that becomes a NAND gate. Okay, so something new, right? So you know an AND gate, you know a NOT gate, you combine these two and you form a NAND gate. Now obviously there is a truth table for a NAND gate, right? So NAND gate is where yes.
So when we have to draw these
Yeah.
illustrations, we have to have the X and the Y on there, or do we just have to draw the actual bullet with the lines coming out?
Yeah, so you need to draw with the variables, right? So as you can see that it takes some input. So this line here takes an input called X. This line here takes an input called Y. And then you have a output line, which is just one number or one line, right? So you have to mention that there is this input called X, there's an input called Y. And you don't need to remember this output here. But you need to give me these two names, X and Y.
Okay.
Yeah.
Thank you.
Yeah. Okay, so let's look at the truth table here, right? So the truth table for NAND gates. So obviously you're combining and you're applying a NOT. So what I do is AND gate is multiplication, right? So you multiply things. 0, 0, 0, 0 multiplied by 1, 0, 1 multiplied by 0, 0, 1 multiplied by 1, 1, right? So right, so now here, so the NAND truth gate, there is an AND there, right? So there is an AND followed by a NOT. So obviously there is an AND here. So if there is an AND, you're going to multiply, right? So let's multiply. So 0 multiplied by 0 is 0. 0 multiplied by 1 is 0. 1 multiplied by 0 is 0. 1 multiplied by 1 is 1. That's your AND gate. But then you have to follow that with a NOT gate. NOT means exact opposite. Okay, so 0 multiplied by 0 is, for AND is 0, and NOT of 0 is 1. So there is a 1 value here. Again, 0 multiplied by 1 for AND is 0, but then you're following that with NOT, and opposite of 0 is 1, so it's 1. Again, 1 multiplied by 0 is 0, but then you apply a NOT gate. NOT is opposite. Opposite of 0 is 1, so there is 1. Again, 1 multiplied by 1 for AND is 1, but opposite of 1 for a NOT gate is 0, so it's a 0. Okay, so let me again go through it. It's very simple, very simple. You just have to understand it once and you'll remember it forever. Okay, so let me just explain you a very simple way. You have two gates here, and NOT. Okay, you have variables x, you have variable y, and the numbers we have are 0, 0, 1, 1, 0, 0, 1, 1, and 0, 1, 0, 1, 0, 1, 0, 1. First you will take an AND gate, then you will take a NOT gate. Okay, so let me ask you, what should I put it here? What value should I put here? Anyone?
0.
0 multiplied by 0 is 0. What should be value here?
0.
Okay. Okay, Lydia. What should be the value here? Lydia.
0.
Emanuela. What is the value here?
1.
Okay. So that's your AND gate. Exactly right. So you were right. So 0 multiplied by 0 is 0. 0 multiplied by 1 is 0. 1 multiplied by 0 is 0. 1 multiplied by 1 is 1. NOT is opposite. So opposite of 0 is 1. Opposite of 0 is 1. Opposite of 0 is 1. Opposite of 1 is 0. And this is your NAND gate. NAND. NAND gate. So that's it. So NAND gate is AND followed by NOT. AND is multiplication. NOT is opposite of AND. So in the exam, I will give you variables X and Y, right? I'll give you these numbers, like some different numbers, different values. You have to calculate the NAND gate, right? You have to make this NAND gate, which is this output here. And you have to present it in a waveform, right? A waveform is your depression, elevation, right? So if I want to present this NAND output as waveform, okay, can anyone tell me if this is a correct waveform for this output? Yes or no?
No.
Why?
I thought it elevates for the one.
Exactly, right? So I just wanted to test you on these elevations and depressions, right? So one should be an elevation. So it should be something like this: elevation, 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 depression. That's a correct output. This is a wrong output, right? So that's a waveform. It's a very simple technique, right? I'm sure you understand it. but it may be confusing, right? If here you have just 4 numbers here, right? So if you have 1, 2, 3, 4, 4 values in the exam, I'll give you 8 values, I'll give you 10 values, I'll give you 15 values. So that in that case, it may get a little confusing. So you have to be very, just take your time and draw these truth tables. And then once you have this output, then ones are elevation, zeros are depression, and you have your waveform. That's all. All right, so I think you do understand the truth tables and these gates, 4 gates. And these are questions you should be expecting in your exam. Okay, so I will also upload the snapshot, right, in your Moodle. So going back to the PowerPoint, so that's our NAND gate, right? So that's our 4th gate, and not, nor, and NAND, right? So 4 gates, sorry, and, or, not, and NAND, 4 gates. All right, so the next gate here, I think it's the last one. Probably the second last one is a NOR gate, right? You see this NOR gate here, right? So NOR gate. So we looked at AND gate, we looked at OR gate, we looked at NOT gate, we looked at NAND gate. The 5th gate is called as NOR gate. So NOR gate again, it's so it has an OR, right? So it's an OR followed by NOT, right? So in AND gate you have AND followed by NOT. N is for NOT, A and D is for AND. Similarly, OR is for OR, N is for NOT. So you have to do OR, you follow that by negation for NOT, and you have a NOR gate, right? So let's do that, right? So let's do an OR gate first. So you have 2 variables called X and Y. 0, 0, 1, 1 for X, 0, 1, 0, 1 for Y. So OR gate you add. So 0 plus 0 is 0, but there is a NOT. So NOT of 0 is 1. So NOR is 1. 0 plus 1 is 1, but NOT of 1 is 0. 1 plus 0 is 1, but NOT of 1 is 0. 1 plus 1 is 2. In binary it's 1, but NOT of 1 is 0, right? So that's your NOR gate. And the diagram for this is OR gate followed by a small circle, right? So OR is this is pointed bullet. So pointed bullet followed by this small circle is a NOR gate, right? So these are 2 special gates. The primary gates are AND, OR, NOT, and the special gates or the secondary gates are NAND and NOR, right? Because there is some like an additional layer, right? So there is a NOT layer on AND, there's a NOT layer on OR, so they're called as special gates. There's some complexity involved with the primary gates, right? Any questions on NOR gate? Are we good? Do you understand NOR?
Yes, sir.
Yes.
Okay, good. If you have questions, please do ask me, because I will be, exact same questions in your exam, right? So please make a note that you are expecting these questions, the truth tables, and I expect you to answer them correctly. Right, so truth tables, these are just a tabular notation for presenting the logic value for all possible combination of values, right? So same things as we discussed. The definition of truth table are, these are notations, right? So these are notations. for presenting a logic value. Now there is a logic involved, right? So you're multiplying, you're adding, you're negating, you're changing um, the output, right? So there is some logic involved, right? You are doing some you are doing some calculations, right? You're adding some functions, right? You're subtracting, you're adding, you're multiplying. So there is a logic. So the way to present this logic in a tabular notation is called as a truth table. So as the name suggests, it's a truth, right? So it would be the truth if you have, say, these two variables, right? If you have these x variables with these values, if you have the y variable with these values, then this is the truth, right? And that's like the universal thing which you should be observing, right? Because if you have these x as, say, a circuit diagram, right? So it's a voltage. If y is another voltage, right, then these are the outputs for voltage you will get if you have these two input voltages, right? In terms of voltage, this is also true in terms of the clock time, right? So you have the CPU clock time. We saw one example before for the CPU processing speed. If you have one input as X, another input as Y, then this would be the truth table for the processing time of your CPU, right? So it's a truth table because it's a general, it's universal output. So these are truth tables, and the diagrams which you saw, right? So there are the illustrations of the diagrams for each of these gates. These are called logic diagrams, right? Logic diagrams. So in the exam, if I ask you to draw a logic diagram for AND, that is just these diagrams here, right? So these are called logic diagrams. And as you can see, previously you had a very simple example, right? So I just had like four values for X and four values for Y. This is a little complex, right? So this is you have more than four. I think you have like 8 values for X and 8 values for Y, right? And more, and you have like you have 3 variables here, right? So you in the previous example you had X and Y. Here you have S, you have A, you have B. So I'm not going to test you with more than 2 variables. I'm going to test you on just 2 variables. So it would be X and Y, but you would have more than 4 values for X and more than 4 values for Y. So I can give you the exact same table here in your exam with 8 values, but I'll just keep just 2 variables, say S and A or A and B, right? So I'll just give you like 2 variables, but more than 4 values for each variable. And you have to make the truth table for that using those gates. All right, moving on. There's something called as a multiplexer, right? So multiplexer is just a name where you combine different gates, right? So in this logic diagram, can you tell me what is this gate name? Anyone? The gate which I'm pointing to. What is this gate called?
Is it an AND gate?
Yes, it's an AND gate, right? It's an AND gate. And again, this is an AND gate. This here is an OR gate. Oh, sorry. What is this? Is this an OR gate?
Yes.
It's an OR gate. Let me check. Yeah, it's an OR gate. And this here is a NOT gate with an arrow, right? So if I go back here, this is an OR gate, this is an AND gate, this is an AND gate, and this is a NOT gate, right? This is a NOT gate. So the idea is, this is a logic diagram. In this logic diagram, you are combining these different gates, right? So I'm combining an NOT gate, its output, it goes into an AND gate, its output goes into an OR gate, and OR gate's output is a final output, right? So whenever you see you are combining these multiple gates that that logic is called as a multiplexer, right? So that logic equation or the flow or the diagram is called as a multiplexer. Multi is many, right? Multi is many. So you're combining more than like one of these gates, and you call it as a multiplexer. And there's a way to present this diagram, right, in form of an equation called as a logic equation, right? So far we saw the structure for gates. Uh, we saw that these are called as logic diagrams. We saw truth tables. We saw waveforms. Another way of presenting these gates is an equation, so called as a logic equation, right? So can you tell me what is this S complement? What gate is this?
Not.
What?
Not.
Yes, exactly, right? So I did mention this before. You see this symbol here, a complement symbol. So it's an opposite. It's a NOT gate. So, right? So S complement is a NOT. So NOT of variable S. And then you have a variable A, you have variable S, variable B. So here you are taking AND of variable A and not of S, right? Because you see a dot symbol, dot is multiplication, multiplication is AND, dot is multiplication. I don't know if I've mentioned this before, but dot um, uh, but dot here is multiply. Multiply is AND gate, right? Similarly, S dot B is an AND gate where you are multiplying S and B. Plus is addition, right? So it's an OR gate, right? So it's an OR between this first half and the second half here, right? So this is just a way of presenting your gates. Multiply is an AND gate, add is an OR gate, uh, complement is a NOT gate, and then multiplication, addition, complement, you can present it in form of this equation, and the output is, say, Z. So Z output is like a final output is equal to all of these steps on right side of that equation. So this is called the logic equation, right? So I'll give you in the exam, I'll give you like a very simple variables, right, or an equation, right? So variables with this equation, and I'll ask you to explain this, right? So if I give you this equation in the exam and I'll ask you to explain this equation, you have to just explain it in your words, in your own words, right? So what I'm doing here is this equation illustrates an output Z, which comes by an OR gate, where you have to first negate or not S variable, then add it with A variable. Similarly, you add S variable with B variable. The output of this and this output of first and you OR that. And then finally you get a Z variable, a final output, right? So just a very simple explanation in your own words, and I'll give you the points, right? So that's called as a logic equation, and also called as a multiplexer, because you're combining more than one logic gates. This is an example, right? So there is something called as MSIs. MSIs, these are some blocks, building blocks. So where do you use, right? Where do you use these gates, right? These gates are used like, they have a wide application, um, the switch, right? The switch, your light switch in the house, right? So you have a light bulb, and the light bulb, you have a switch. So I think you switch it up, it turns on the light. You pull it down, it switch off the light, it turns off the light, right? So it's an on off, right? So on of is a gate, right? So that's one application of the gate. So logic gates, they have a wide range of applications. Simple circuits, it can be multiplexers, it can be CPUs, right? So wherever in whichever case, right, or situation you want to control the system, right, control the flow of information, you use a gate. In biology, right, in biology you also have these gates where there is like one process where you generate ATPs, right, adenosine triphosphate molecules, right? So these are the building blocks, the energy which is needed for humans to perform the task, right? The energy. So that ATP is produced by controlling the information, and that also can be compared to these gates, right? So gate is a very essential and very uh, basic mechanism to control the system. It can apply to like circuits, it can apply to computing systems, it can apply to human um, physiology, right? So there is a wide application. One of these is called MSI, building blocks. I won't go into details on what is MSI. If I asked you to give me two examples of of um, of of using these gates, you can give me one example as like say light bulb, right? So you have electricity, to control that electricity, use these gates. You can give me another example of computers, right? In computers, you have to control the flow of clock time, right? A clock time or processing speed. That is another application of using gates. In biology, the ATP synthesis is again controlled by some of these gates, right? So these are 2-3 examples of uh, application of gates. Another example would be transistors, right? Transistors are digital building blocks. In transistors, right? So you have these electric chips. In the chips, you have these transistors which control the voltage, right? Voltage of your electricity or your current. That is again controlled by these gates. So transistors would be another example of gate applications. Um, right, so one example I gave is this switch, right? So you have this light bulb and you switch on, you switch off. You can say on as one, right? So you tag on, switch on is as one, switch off is as zero. When you have one, then the flow, there is a flow of current. Then you have zero, then there is no flow of current, right? So so this is where you abstract the signal, right? So abstraction is where you summarize things, right? So you summarize all of the flow as one and you summarize all of the no flow as zero, right? So this is just way of presenting your gate in an electric circuit. This is another example, bipolar transistor inverter, where you apply a NOT gate, right? Um, uh, right, so this is one example where you are applying like more than one gate, right? So again, just an example, I'm not going to go into details. It's called as transistor logic, TTL, right? So you are applying that more than one gates to control the flow of your current through transistors. Well, it's called TTL. Another is CMOS, so complementary metal oxide semiconductor field effect transistors, right? So these are different transistors which are used to control the flow of current or voltage, right? So each of these systems, they use a different logic. So in this case, you can see that there is a NOT gate or an inverter, And I guess you also have a NOT gate or an inverter in bipolar transistor inverter, right? So these are different systems of using different gates. Um, and you can give me these examples, or you can give me just examples, simple examples which we discussed uh, uh, with the flow. Okay, what's next? um, Okay, so I just skipped some slides here. Those does not seem to be important. Just some more examples, and I don't want to go into details of those examples. So let's look at this slide number 23, which is the levels, right? So, okay, so now we have defined an idea where you are controlling the flow of information using these gates, uh, right? So, I mean, how good of a system would that be, right? So with just gates, right? So I want to control the flow of information, and I'm just using these gates. So will that be like the most effective system, right? So will that do what I'm asking it to do, right? Because a system is a very it's there are many variables and many factors, right? So it's just not gates which can define a system, because the system can be influenced by its environment, right? So you have different environments. So for example, in this slide you see that there are these different factors like temperature, right? So if you have a circuit which is present in a heat environment, right? So in a hot temperature, and if you have a circuit which is present in a cold temperature, with same gates, right? The same gates I'm applying for both these circuits, they will act different in different environments, right? So in heat, you may have a very nice flow of information as expected, but it may not work the same way in the cold environment, right? So the external factors, they influence the system. So the gates are important, but more than that, the factors which control that environment also define the flow of information, right? So you can have the temperature, you can have, say, the production process, right? Or you can have the phases, um, or you can have different voltages surrounding that environment, right? So you need to understand that gates are important, but there are other factors which also influence the flow, which are the temperature or the different phases, right? The material of your environment, right? So if your circuit is like made up of say silicon, right? Silica, and another circuit is made up of like say tin, right? So you have a one circuit which is made up of silica, another circuit which is made up of tin or some other metal, right? Mercury or something else, right? But the gates are same. I'm using say AND gate in silica, and I'm using the AND gate in mercury circuit, but the flow may be different because the factors, the other factors, they do influence the flow, and the gates are not ultimate, right? They are not like everything, right? So people have understood this concept, right? So obviously there is you can influence things with the gates to at level, and that level is called as a threshold or a margin, right? So that is something which has been given in this slide. So there's a margin, right? There's a noise margin, there's a threshold with which you can control the flow with gates. But if you go beyond that threshold, the flow may be different, right? You cannot control that system, right? And this threshold or this margin, this noise margin is defined by the factors influencing the environment, right? So the temperature or the material of that circuit and so on, so on, so on, right? So obviously you can try to push it, right? So obviously you have defined a margin that I can go till that margin. So I can apply gates and push, I can push my gates to that margin, right? So I can use maximal, right? So I can do a maximal usage of those gates. I can push the gates to that margin, to that threshold. Now that can be purposeful, right? That I'm doing that on purpose, or it can be accidental. The system itself can push it, right? So say you have like let's give you an example of a cylinder, right? So you have a cylinder, and the cylinder is filled with water, right? Cylinder is filled with water, and there is an air, right? So I can add in more water, so the pressure will be pushed up. So that's a purposeful push, right? But the system itself, the cylinder itself, is trying to get rid of some pressure, right? So that is like an accidental, right? So purposefully, if I'm filling in water, then I'm pushing the pressure or the system towards a margin, towards a threshold. But system itself also is trying to reduce that pressure. So briefly, there is a margin, there's a threshold. You can push your gates to that threshold. That is called as a purposeful push, or that push can also be accidental by the system itself, right? So these are a few things which you need to know. These are some, I would call it as some properties of your logic and circuit. And I think these are some examples on these margins, right? Noise margins. So I can give you some time to read on these remaining slides, but make sure you understand the truth tables, the illustrations, and I guess there are like 5 or 6 gates, right? And the waveforms, right? So do practice on these truth tables, right? So you have 4 values in X, practice with like 8 values, and what would be the output for that? And those would be the questions you would be expecting in the exam. Okay, so I think we just have 2 minutes. Do you have any questions so far? Any questions?
No, sir.
Okay, so all right, so let's do this. Go through the PowerPoint, and we will meet up again on Monday and next week. And if you have any questions before that, do let me know, right? And in the next class, I will go on to the next PowerPoint, right? So the rest of the slides are just some examples and some properties of circuits. So I'll just ask you to read them, right? Some properties. But in the next class, I'll go to the new document, lecture 2 document, right? Which is uploaded on your Moodle account. So go to that, and then I'll see you on Monday. That's all. Bye bye.
Bye.
See you next class.
Yep, bye.